Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello everybody. Welcome to another episode of Ask Us Anything about electrochemistry. I'm your host, Dr. Alex Peroff. My colleague, Dr. Neil Spinner, is out today, so it'll just be me. But for those of you who are regulars and for those of you who are new, thank you for joining us for another episode of Ask Us Anything about electrochemistry. These live streams are designed to be a way that you, people in the electrochemistry community or researchers who are trying to learn electrochemistry or have a hard time understanding certain concepts behind electrochemistry, can just ask us any questions you have about electrochemistry. So most of the time, the questions that are best appropriate for this kind of live stream are questions kind of in between these two extremes. Sometimes we'll get questions that are just like, explain EIS, and that's a topic for an entire webinar series, which is something that you have access to if you're a YouTube member. And some questions are super specific to like what's the rate constant of a specific molecule in a very specific electrochemical system. But there are a lot of questions kind of in between those two extremes of specificity and then broadness that are actually that we can answer, and that we can try to provide a little bit of clarity, at least with regard to understanding some of these concepts. This live stream is broadcasted through a platform called Restream, and it's on YouTube and Twitter. We found that there's maybe about a 20-second delay between what you see in front of you and when we actually, and when a chat message comes up. So just keep that in mind when asking questions. If you are a YouTube member, thank you for being a YouTube member. You help support the creation of this content. If you are a YouTube member, you also don't just have the opportunity to type a chat message in, but you can actually join this on Restream and talk to us, and also share your screen, share data, if it makes it easier to answer an electrochemistry question. An apology in advance for those of you who are, these are all kind of like YouTube or Twitter names, so it could be anything. So if we mispronounce your name, just an apology in advance. So with that said, we usually go for about 2 hours. We'll see. It's always based on how many people are there. But we'll see what questions we can answer today. So Chris Georgie says, good morning to you. It's about 1 in the afternoon here in North Carolina, but wherever you are, whoever, some people are in various different places in the US or across the world watching these live streams. Okay, so there was a question. There are actually a handful of questions that we got over the week, so you can post these questions over the week. Also, if you are watching this, I always forget to mention this, if you are watching this after the live stream has aired, we usually try to put the questions in the description of the YouTube video so you can look through them to see, and then click on the one that you want to have answered or look at. So there were some questions that came about over the week, and maybe even some questions that we couldn't get to last time. One question that came in actually several hours ago, maybe about 17 hours or so ago, is from Anindanath 8136. This is kind of two parts, just because I couldn't get the whole question. And this was a YouTube comment related to cyclic voltammetry. And this is actually just a comment from something I said. He was asking about, again, this relates to the nature of like oxidative and reductive currents and the potential with which you observe them. So he says, quote, when a reduction occurs, the standard potential of species in solution is lower than the potential of the electrode, governed by the potentiostat. That way, electrons will flow from the electrode to the species. So this is just giving us some context. And then it continues to say, I guess for the species in solution to get reduced, the standard reduction potential of the solution should be greater than that of the electrode, as higher reduction potential means higher tendency to get reduced. Can you clarify? So I want to kind of draw upon a little bit of a picture of electron transfer, at least my understanding of electron transfer in with regard to just a cyclic voltammetry, or when you apply a potential, because this is something that we commonly do not understand, and it's even something that I try to understand but don't always do it. And so let me just make sure that I'm sharing my screen here. Let's make it a little bit like this so you can see. All right, and also I want to keep an eye out in case new questions come in. But basically, when it comes to electron transfer at an electrode surface, there are a couple things that we want to keep in mind. So let's say we have an electrode. This is the potential of an electrode. So this is the square, or this is a square representing the electrode. The kind of y-axis here is the potential. And let's say that this is kind of the level that it's at, right? This is the level. And then we commonly paint a picture of the HOMO-LUMO gap, or the HOMO-LUMO of a molecule, something like this. So you have some lowest occupied, highest unoccupied. Maybe that's reversed. But the orbital here is unoccupied. The orbitals here are occupied, and you want to get some kind of electron transfer to occur. And so ideally, let's say if you want to oxidize the species, you want this electron, maybe this guy, to go into the electrode. And so you would imagine decreasing the potential, so decreasing the potential such that an electron can hop in. That would be an oxidation. Or conversely, if you wanted to eject an electron into this orbital, you would increase the potential, right? And that's ultimately, that's like the simplest picture for describing electron transfer on the electrode surface. Now, one thing that's very important, and something that I learned about actually earlier this year, just kind of a better picture with regard to this. Also, if you guys can hear me, I just want to make sure people can definitely hear me, which is good. I think there hasn't been any comments. One thing that's very important that a lot of people mistake is that they believe that an electron's got to go from higher to lower energy for an electron transfer. Like, oh, this thing's got to go high to get this electron to kind of jump into the orbital, or this one's got to go low so that this guy can jump into the electrode. And that's not true. Electron transfer always happens when you have energy at the same level. It's all the same level, right? So only when the orbital is at the same level of the electrode do you get an electron transfer between the electrode and the molecule. So that's a very important distinction. And this picture that we have of the orbital, like this orbital makes sense for something like atomic orbitals, right? Atomic or molecular orbitals in the gas phase, right? So only in the gas phase do we get a picture like this. Let's just call it gas phase. But when you're in the aqueous phase, when you have solvent that's around your molecule, your analyte of interest, you actually get a little bit more of a continuum. It's not a single state. You actually have something. Sometimes we like to draw these kind of little like semicircles. So let me kind of erase this picture. But you tend to get something that looks a little bit more like this. So you have these kinds of these states, sort of say, and there's all kinds of little states that make up a bit of a continuum, sort of say. So if and I guess there's many ways to draw this, but this comes from Marcus theory, which is something I still need to review. But like when the electrode potential is here, there are a series of states in this region that can undergo electron transfer. All these can undergo electron transfer. And as you change the potential, as you raise or lower the potential, you can access more states. You get more electron transfer can go if the potential is at this point. And another thing that's hard to describe in this picture is that it's not that this level necessarily goes up. It's like the whole thing, this whole thing in brackets goes up. It goes up and it goes down when you change the potential. You're not actually adding more electrons into your electrode by doing this. You are only adjusting the whole bar relative to the energy of your molecule. So that's really the important thing. That is something that actually I learned earlier this year as kind of a picture for electron transfer and how people think about this. And Chris is actually saying, like, yes, orbitals don't exactly capture the reality of an electrochemical system, which is exactly the point. And a lot of people in academic talks all over usually draw that kind of picture with direct orbitals that do it. But it's important that we understand that it's really a continuum because you have solvation. It's because you have a solvated analyte. So, Chris, that's a great point. So I have a question from Alex Meyer. What in graphite balances charge when accepted? And that is, say, accepting of lithium ions. So Alex, what I'm gathering your question is you have maybe a graphite rod as a counter electrode to your electrochemical system. You have your working electrode that's, say, accepting, the lithium ion, and then the counter electrode's also doing something else. And I'm assuming this has maybe a little bit to do with batteries. And unfortunately, I'm not the best lithium ion or battery expert. Neil is that guy. The thing that I kind of have questions about always with these systems is we talk about the intercalation of lithium ion into the battery or into the anode or the cathode. But I feel like there still has to be an electron transfer. Like lithium ion needs to become like lithium metal or lithium 2+. Like for current to flow, you also need like an electron to flow, or you need an electron. Maybe I'm wrong when it comes to that, but that's something that has always been like an ion moves across the electrode surface. Does the potentiostat notice that or observe that? That's actually something I'm kind of like, I don't want to say on the fence about, but like I need to wrap my head around it a little bit more conceptually. But generally speaking, let's say there's some electron transfer. What's the graphite doing? Well, the graphite balances charge through a number of mechanisms. One is actually the non-Faradaic charging of the electrical double layer. So that's one form of charge balance, sort of say. And then usually it will be something at the electrolyte, some kind of reaction with the electrolyte that will also continue to do another part of the reaction. So this is probably, I mean, I'm assuming this is all about batteries because I think it's cathode materials are usually graphite, and anode materials are usually lithium. But yeah, I am not 100% sure I know what the counter reaction is when it comes to a battery. That's something I need to learn a little bit more about, and perhaps that's something Neil can discuss a little bit later when he's back. He's hanging out with some family today, and I think next week we'll both be back before in the U.S. there's the Thanksgiving Day holiday, and then I'll be out for a long time. So we'll see how that goes. Also, yeah, and Chris says that lattice dynamics are not intuitive. Yeah, I don't fully. It's like, okay, I understand the idea of like, okay, the lithium intercalates into it, but does that mean there's a charge balance going on or an electron transfer occurring? So I should probably study more batteries and get better at electrochemistry. Let me also check if there are any interesting questions. Doesn't look like there are anything, at least in the Twitterverse. So I'm happy. Just let's see. I'm gonna see if there were a couple questions. There was at least a comment from last week from Umar Latif. So I'd like to get to this. Umar says, nowadays, some review articles state that galvanostatic charge-discharge is a more reliable technique than CV to calculate the capacitance or capacity of our material. And then part 2 of his question or comment was, although CV data is more valuable to quantify and identify the charge storage mechanism through power law, Dunn's method, and Aridizoni method. So Umar made a comment about this, but there wasn't necessarily like a question about whether or not, well, is one better or worse than the other. And this may have been a comment from at least the last Ask Us Anything About Electrochemistry live stream, which we were talking a lot about galvanostatic charge-discharge versus CV versus EIS. So I think that was simply a comment. I actually had not heard of Dunn's method before. I'd have to look a little bit more into that because I'm slightly on the fence about Dunn's method, which is a method that describes, basically is a way of determining the percentage of capacitive current versus like Faradaic or diffusion current for in a cyclical thermogram. Kind of on the fence about those types of results. So I am. It basically puts like a mini CV within a CV as being related to the charging, the capacitive current, and like a small portion of everything else being associated with the diffusion element of the current. And I'm not 100% sure that that's, I don't know how to say that it's correct or incorrect. It just seems a little odd. I would have to do some research on it, and actually do some experiments, which I may try, like cyclical voltammetry simulation. Okay, let's see. Doesn't look like we have any questions so far, so I'm happy to just wait to see whether there are any questions or comments. One thing that happened recently was Neil and I were actually at Virginia Tech doing an EIS workshop. So that was actually a fun experience. And we're hoping to do some workshops later in the future with other universities. And so if you're from a university and you'd like to have us run a workshop with you, we'd be happy to do that or work with you on that. Although our schedule is starting to get a lot busier. So, but with that said, we can wait a little bit and see if there are any questions that come in into the chat. And if, of course, there are any topics that people would like to talk about, I'm more than happy to do that. But let's see. If there's not a lot of people on, that's okay. There's always sometimes there's just not a lot of people who are asking questions, and sometimes you just have to wait for a better or a more interesting or some kind of different time. One thing that I would like to do is I'd like to share a screen and give you guys like just a promo while waiting for our upcoming podcast. So I'm actually gonna show that, and this will be another thing to do while we wait for any questions to come in. And just give me 1 sec. I want to showcase this. All right. Okay. Make sure that everyone can see this. All right. Yep. So we're launching our our YouTube, not YouTube, but our a podcast. So it's gonna have a major public release on January 4th. But for all of you YouTube members, tier 1, I think at least tier 2 members, you'll be able to get early access just in a few weeks, actually, beginning of January. So that will be something exciting to look forward to. Neil and I have been working on it for a while, and this month we're going to try to get the last few edits to make sure that the podcast is ready to go out. Let's see. So Fernando asks a question. So Fernando, thanks for answering questions. Expert 2. Unfortunately, I have to do circuit models myself, so I joined tier 2 binge watch webinars. I have a couple questions. Let's see if I can answer them. Let's see. Do you have some sensical range for SPEs or electrodes of that size? Not something specific, just to give me an idea that the values of the circuit elements also make physical sense. Okay. All right. So that's a good question. So basically, Fernando, what I'm guessing here is what you're asking for is, do we have any like EIS data for SPEs to kind of just make it's just as like a test system? Do you have a test system that I can make sure that I'm running my system and I'm getting normal results that kind of make physical sense? That's a great question. So, and let me see. I just want to make sure like there are SPE screen printed electrodes, but there's also regular electrodes to give you a sense. Okay, so I have worked with a couple different types of systems, but like one system that comes to mind is ferrocene, just the oxidation reduction of ferrocene on a normal 3 millimeter outer diameter, 3 millimeter outer diameter glassy carbon electrode in a non-aqueous solvent such as acetonitrile. So when you're working with something like acetonitrile with glassy carbon working electrode, platinum counter electrode, and say a silver wire, or if you have a frit, you have maybe like a silver nitrate solution, silver nitrate as the non-aqueous reference electrode. Depending, of course, on the position of the electrode, you're going to get, you may get several hundred ohms, 200, 300, maybe even 500 ohms of resistance as the solution resistance for like a more traditional 3-electrode cell. Of course, it depends on a lot of factors, but that's kind of the order of magnitude with something like a CO-nitrile. When you work with systems like tetrahydrofuran, THF, as the solvent, you can have thousands of ohms of solution resistance. So that is a thing you can do, because I know you're trying to figure out about like circuit elements and whether they make any physical sense. So that's one thing. Between 3 and 5 millimeters outer diameter, the capacitance of the electrical double layer should be in the microfarad range. So I usually say between 10 and 30 microfarads is a relatively normal capacitance to get for just a regular 3-electrode system. The electrical double layer capacitance is a massive number, considering the size of something that's like 3 millimeters or 5 millimeters in outer diameter. So those are a couple things I would like look for to make sure that you're having some sensible ranges for the electrodes in that size regime. Other things that you can do to kind of give yourself confidence is use a dummy cell for EIS circuit fitting. And a dummy cell is sometimes it's not actually a dumb cell, it's actually a very smart cell. But a dummy cell is a circuit, right? It's a circuit with known resistors, capacitors, all those types of things. And you can buy them relatively inexpensive. You just need the circuit elements. And when you put them all together and you run EIS of that circuit, and you put it, you know what the circuit is, you know what the values are. You can then try to do circuit fitting, especially of the model that you're using. And you can try to see, like, all right, when I try to do a circuit fit, am I getting normal results? Or am I getting results that are related to the actual physical circuit that I'm working with? I always recommend doing a dummy cell test if you're new to EIS and you're trying to do stuff. Demonstrate that the instrument is working properly, and that you are able to simulate and get very good or close numbers to what you're actually supposed to get. Neil mentions this quite often, but you should absolutely, whenever doing any circuit fit, do a Kramers-Kronig analysis. And basically, let's see if I can at least, maybe not necessarily demonstrate it, but if you're using Aftermath software, let me just make sure if you have Aftermath software. I don't have any, let's see if I have any data. So if I open an archive that just has some, I think he gave me some sample EIS data, but basically you want to do Kramers-Kronig. So once you have EIS data, you just want to click Kramers-Kronig. And you want to look at things like your chi-squared. So this is just to make sure that your EIS data is valid. That's number one. So making sure that your EIS data makes physical sense is one thing. Making sure that your EIS data is valid is the next thing. And if you're getting like a very low, like below 0.001 or something, or 0.01 chi-squared, that's usually very good, or something that we look for. So the Kramers-Kronig analysis is very helpful. I don't know if you've gotten to that part in Neil's webinar series, but doing that Kramers-Kronig to make sure that the EIS data is valid, and then doing your circuit fit, looking at things like chi-squared, and then comparing it with what you believe to be reasonable values, will be helpful as you kind of validate your EIS data. So, Fernando, let me know if that made sense, and whether or not you have any further questions or further analysis. But hopefully that was helpful. Kramer's Kronig, dummy cell, and then my personal experience with a 3-electrode system in an organic solvent, acetonitrile, you're in the hundreds of ohms for something like the solution resistance, and double layer capacitance is in the microfarads range. 10 to 30 microfarads generally is like a good double layer capacitance value. Can always change it a little bit, but that's just ballpark in the realm of making physical sense. Okay. All right, gonna check Twitter. Nothing, no questions. Let's see. So, good thing everything on the Twitter side looks like it's under in good standing and working order. All right, we have another question from Ajazul Bashir. Let's see. The question is, how does the local environment at the electrode-electrode interface look like at OCP? Like, is there only a double layer or some Faradaic process, charge transfer? Sorry, I misread that. Like, is there only double layer or some Faradaic process like charge transfer is also there? That's a great question. That's a very, very good question. I would go so far as to say that I think it for the most part will depend. It'll depend on a lot of things. So let me explain. So OCP, the open circuit potential in your system, just because you're at OCP, it doesn't necessarily mean that electron transfer or charge transfer isn't happening. If I put a piece of copper in a solution, I'm going to start oxidizing the copper. And that's because thermodynamically, copper naturally oxidizes, or silver naturally oxidizes. I don't actually have to apply a potential for that process to occur. So you can have Faradaic processes occurring at open circuit potential. Okay, something to keep in mind. You also will form a double layer. There's absolutely an electrical double layer, especially on a conductive metal surface. At OCP, it certainly will look different because even at OCP, conductive metals naturally have charge. They're naturally charged at the surface. And doing things like cyclic voltammetry, doing things like chronoamperometry, applying or changing that potential will change the double layer. There is a charging of the double layer as more or less negative or positive charge is built up at the surface. You will have that. So the local environment at the electrode-electrolyte interface at OCP will actually kind of look a little bit like it would at any other potential. Of course, the other elements, such as if it's at a potential where a Faradaic process is occurring, you will still have Faradaic processes occur, even at open circuit potential. Oxidation, rusting, that will occur at OCP, like for iron. Like you dunk an electrode in your solution, no applied potential, but you'll have a non-zero current. And that's another important thing about that's another thing about OCP is OCP is also very different than doing, say, galvanostatic, doing a galvanostatic experiment at zero current, because OCP is a very passive, like I'm just measuring what the voltage is. But galvanostatic experiment where you set the current to be zero is forcing the potential of your system to be such that no current flows. So it's forcing it into a system, and that is actually different than just OCP. It's something to keep in mind. But that's a very good question, and I'm more than happy to elaborate more on it. But you will definitely have an electrical double layer, especially if it's a metallic, and definitely conductive electrodes have this. And you may have a Faradaic process if the system itself, the kind of the delta G, if it's thermodynamically spontaneous and kinetically favorable to have an electron transfer at OCP, that'll also happen at OCP. So I hope that was helpful. Okay. And if there are other questions, also keep an eye out on Twitter, because they don't have the best way of describing things. But I will continue to wait some more. I probably go through questions a little bit quicker than Neil might. But I also want to make sure that I'm providing sufficient feedback for people if I'm answering their question correctly, or if they need more clarification. Please continue to have conversations with me, even if I answer things perhaps a little bit quickly. All right, let's see. So Fernando has a follow-up. Thinks it's pretty useful. The KK is below 0.01, so that's the chi-squared, which is pretty good. The Warburg's value, where's the issue? Also, is there a specific way to cite aftermath, or mentioning it in the methods, or mentioning it in methods is enough? So the Warburg value, that's a very good question. And I would say the only way to look at a Warburg element and understand whether it makes sense is in the webinar series. There are equations that describe the relationship between, say, a Warburg and say the diffusion coefficient. So let me look. I need to find if I think I'm going to try to borrow some of Neil's. I think Neil had a slide on this that allows you to take the Warburg element and then you can backtrack a diffusion coefficient. So let's see if I can't find that. So of course these are his slides, so I don't know enough about it, but if you give me a second to try and find, I'm just gonna take a quick look and see if I can't find stuff about Warburg elements. Okay, it's not that one. Give me a sec as I look for it. I think it's 2. Okay. Okay, all right. So I'm going to, all right, I think I found it. So I'm going to share my screen quickly. All right, so hopefully you can see this. This is from one of Neil's webinars, and he's talking about Warburg diffusion in the infinite case. This is the case where bulk, kind of diffusion is considered infinite / semi-infinite. So this is like your electrode, and then you have like at least, I'm just gonna say like an inch of solution between your electrode and the glass, which is relatively easy to achieve. But yeah, the question is, what is this Warburg? Right? What's this Warburg element, right? There's the impedance associated with the Warburg, and then there's what is a good value for the Warburg, coefficient. And I'd say the best way to determine if you have a realistic Warburg value is to actually plug in a diffusion coefficient like this dA, or square root of dA. And diffusion coefficients tend to be on the order of 1 × 10⁻⁵. So that's the, and I forgot the units, it's like centimeters per, I think it's centimeters squared per second. I don't know, I can't remember if it's an area or just a line. But plug that 10⁻⁵ 0.5, square root of that, times, say, 1 millimolar times, some fraction, maybe 0.001 centimeters, Faraday's constant squared, maybe 1 electron transfer, R and T, and then you'll get a number for your Warburg, and that will give you a sense of like, okay, this is the right order of magnitude for my Warburg circuit element. So that is the way I would go about determining if you have a normal if your Warburg value makes sense. Okay. And is there a way to cite aftermath? I think citing aftermath, you'll probably, you might just say Pine Research Instrumentation aftermath circuit simulation software was used for this fitting. So that's how I would cite it if you're not using like a Pine potentiostat, for example. But yeah, I mean, actually, that's you do raise a good point, because actually we are generating a lot of software features now. We actually have cyclic voltammetry simulation. That's like a new software that we have and are continuing to develop. So and I put the version of aftermath as well. So aftermath. Let me actually try to just put it there. So in this case, this is actually, I don't know if you'll be able to see it. Let me double check to make sure. Okay, so you probably can't see it very well. It's a little hard, but the version of aftermath is here. It's also in the help. So if you hit help about, you will have something that looks like this with the version. And it'll say something like Aftermath Electrochemical Studio or something along those lines. So, but that, Pine Research, Aftermath Electrochemical Studio, and the version, you can even say if it's 32 or 64-bit, but that would be the best way to cite the use of Aftermath. So hopefully that helps. All right, good. We have a couple more questions coming in. Let's see. So just a follow-up from Ejaz ul Bashir. Thank you. That was helpful. But then how do we say that the net current at OCP is 0 if Faradaic response reactions are also taking place? So if that's the case, you probably can't. You probably can't actually make that, because you're right. If the net current isn't 0, then yeah, you're and to a degree, your OCP also wouldn't be changing. But here's something that you can do to make sure. Now, granted, I don't think that you are using something. Of course, I'm making a guess. You're probably not using something like copper or silver, and where it oxidizes naturally, or iron that oxidizes naturally. You might be working with just glassy carbon in an aqueous solution or something along those lines, where truly there is no net current. So what you can do, a thing you can do is you can take the OCP. So you measure the OCP over a period of time, and you make sure that the system is stable. It should be, the OCP should not be changing. And then what you can also do is you can run a galvanostatic chronopotentiometry experiment. So I'm going to minimize this. I'm just going to show you what this looks like in our software, just so that if you go to experiment, there is chronopotentiometry. Okay. And there's a lot of things. There's like a induction period and there's a relaxation period, but the important period is this electrolysis period. And you want to set this to 0. So set the current to 0, and then you may want to run this for, say, 30 minutes or something like that. And then you're going to want to keep the voltage range, just keep it however you want, plus minus 1 volt should be fine. But when you perform this experiment, the voltage that you measure from the chronopotentiometry should be basically equal to that of the OCP. And of course, all of this has to be with respect to your to like a reference electrode or to the OCP value or something like that. If it's with respect to, if you're measuring the chronopotentiometry of OCP with respect to, or if you're measuring chronopotentiometry with respect to OCP, then you should get a value of 0. Because if the voltage that you're measuring is anything but 0 or close to 0, then some current is flowing. So that would be the way I would check to make sure that you don't have any Faradaic current that's flowing in your system, is that OCP, the OCP and the chronopotentiometry data are the same. And if they're different, then you do probably have some current. But make sure everything kind of normalizes for you to make that claim. So I hope that was helpful. Please let me know. Okay, so just going through these. Let's see. Giannis Rio says, "Hey guys, I want to perform an electrolysis for CO2 reduction. What is the most easy way to have a membrane-less 2-compartment cell?" So if you, well, Giannis, I think by virtue of without having a membrane, you can't really have 2 compartments, sort of say. And what the membrane is can change. Most people actually will do something like they'll use like a glass frit. So you don't need to have like a membrane selective electrode like Nafion or something like that. You can use glass, and it just limits how quickly molecules move back and forth, but it's not limiting things based on ions or electrostatics or things like that. So there are things like, I'll just do a little shameless plug here, but let me find a simple H cell. But we have a variety of different kinds of H cells. So I'm just going to share this with you. But this is just a simple H cell. And this H cell, and let me just make sure that you can see it. But this H cell just has glass. It's just glass between these 2 compartments. And that's it. So it's not like a traditional membrane in the sense of it being something like Nafion, or it's an ion selective membrane, but it's just glass. That's it. And so this is a simple H cell is probably the best way to do it. And if you are on the Pine Research website and you go to standard H cell or simple electrochemical H cell, type that into Google, you'll be able to find it if you want to look at a similar part. And you can do things like, people do this to do things like electrolysis. So hopefully that answers your question, Giannis. And if you have further questions about it, please let me know. Okay. All right, from Dualies. Right. Sorry. Is there a typical OCP value that one should aim for before running a non-aqueous CV? Sometimes I observe OCP values jump between tens to hundreds of millivolts between experiments. I have experienced this as well, Dullies. Don't worry. This is kind of I've seen the same thing, and yeah. So non-aqueous electrochemistry is a bit challenging. It always has some challenges to it. It's just not. It tends to not be as stable, say, as your normal aqueous phase. So what I usually do is you ideally want to have the system settle for OCP. So your OCP, it starts off at some value, and then it maybe decays, and hopefully it reaches some kind of relative steady state where it is only jumping in the tens of millivolts range. That's probably what you want. But for a cyclic voltammetry experiment, I would highly encourage you to use something like an internal standard when doing non-aqueous electrochemistry. And what I mean by an internal standard, which maybe this is something you're familiar with, I'm just going to hide your thing for a minute. So let me just hide your question just for 1 minute. And if we go to PowerPoint, what I mean by an internal standard, which you might know, you all might already know about this, but if I have my cyclic voltammogram, voltage, current, maybe your voltage is here or something, and you're studying something, and you get some interesting, some interesting CV because you have some really, really cool molecule. Well, what you want to do is you want to have a CV that's like here. Let's just say, this is a terrible CV, but you want to have a CV that's here. That is your internal standard. I'm just kind of highlighting it green so we can see it. And this would be your, not comment, sorry. Text box. This would be your internal standard. All right, that's this guy right here. So your internal standard is the is just a molecule that has a known redox potential, and if this shifts in your or during your experiment due to OCP or drift from your reference electrode or something like that, you know what this potential is. And so if you see the potential of these guys moving, if these guys start to move, this guy should also move. And so you'll now have a much better, that's why you see a lot of people do like this whole versus of FC plus, because they use the ferrocene redox potential as their internal standard. It's like a well-established potential, and all they would end up doing is they would take whatever values for the redox potentials that they're getting, and they would reference it with respect to FC plus. So they would actually, in this case, add, so let's say this was like 0.1 volts. Let's just say that. They would take whatever this potential was, and they would add plus 0.1 volts to it, and that would be the potential with respect to the ferrocyanide, or not ferrocyanide, the ferrocenium redox couple, and that will give you, that makes it so that if OCP shifts around and jumps around, or if your reference potential is shifting or jumping around because you're in a non-aqueous system, you at least know what the ferrocenium redox potential is, and you can keep and maintain that standard. So I want to delete this because I don't want there to be any comments. But hopefully that answers your question, and we can again talk more about it if you have. All right, so let's just kind of go through this. Let me just see. Oh, thank you. It was also, but then how do we say that the net current, I think I answered this already. Yes, I answered this one already. I think maybe you just typed it in twice, which makes sense. Let's see. Also, Chris is also asking some questions, or not asking questions, but kind of giving us some information. We enjoy your contribution to the chat and managing the chat. We should make you an admin or something like that. See, I think I might have an irreversible process occurring. I see peaks, but they are not textbook reversible in shape. Let's see. Let's see. Dullies, have you evaluated the irreversible process expected in the system? So Dullies, let me mention a couple things to do when it comes to determining whether or not you have a reversible or irreversible process. So the main thing, probably the most important thing you should do, is you should do a scan rate study. Okay. So let's go back. Let's review, start inking. Let's erase all this stuff and delete this. Oops, delete this. So when you do a scan rate study, what you're observing for your CV, if you have an irreversible system, is you're getting something that looks like this. And then there's nothing, right? You know, there should be something that's like here, right? But it's missing. Well, what you can do is you can do a scan rate study where you change, you do like 100 millivolts per second, you do 50, a second, you do 50. You also do a couple other things. You try to also do maybe 1 volt per second, and you try to do maybe 5 volts per second. And what this does is you'll get more current. When you start going faster, you'll get like way more current. But you might start to see like that. Or you might start to see like, it may even be further out. But if you change this, there's a chance the irreversibility of your system, and this is something that you have to determine or test, is that there may be a chemical reaction that's occurring. There may be some kind of chemical reaction that's occurring. I'm going to do another thing to hopefully help demonstrate this. And that is, let me share, we can do a simulation of this actually. So we have a cyclic voltammetry simulation software. And if you have, say, an electron transfer process, and let me just put some numbers out here, and let's just do cyclic voltammetry. Let's also do this. So let's say you have this. This isn't what you're getting. Let's say this reaction is super, super fast. And simulate. Right. So, and it may even be faster than this, right? Maybe it's much, much faster. So fast that you're not getting any of your reversible current, right? So this is a case where maybe your solvent, so in this case I have a reaction of A plus an electron goes to B. It's got a very fast heterogeneous rate constant. That's what we're assuming. Alpha is 0.5. But there's a chemical step that B very rapidly goes to C, right? So B very rapidly goes to C. Well, I'm sweeping at 100 millivolts per second. Actually, let me make sure that this is kind of big enough so people can see this. Now, if I go to like 1 volt, 1,000 millivolts per second, and I simulate this again, actually, this kind of made it worse in a way. Ideally, when you start changing the scan rate, you should start to observe some extra. Let's see. What if you go 50 millivolts per second? Oh, that was strange. I'm expecting a little bit more of this to show up. Yeah, okay, so I think the first time I did it. So we are starting initially at plus 1 volt, which also makes me think that this is also a little bit too high. So let me simulate this again. Let's make this a little bit. Yeah, there's a good chance something got stuck. All right, so if I go here, if I start sweeping faster, let's try 5,000 millivolts per second. Start to see a little bit more. Let's go even faster. This is a simulation. Okay, so when you start going super fast, 10,000 millivolts per second, 10 volts per second, you start to see some of the reversibility. And of course, we're now getting more ridiculous, but at 100 volts per second, you'll be able to start to see this process, right? The reversibility will start to come back as you're going so fast that you're fighting against this forward rate process. That is one thing that can be happening. Another thing that can be happening is if you have a regular electron transfer, and again, we'll fill these in. We'll simulate it. So we have just a normal CV, normal sweep rate. Now this is your duct. Looks good. Looks perfect. If I start to make the heterogeneous rate constant slower and slower, so instead, that was 1, let's go 2 orders of magnitude. I start to elongate this voltammogram. Say it's really, really slow. Now it's really slow. There is a chance, and I don't know what your parameters are, but there's a chance that if you sweep here and you're not sweeping back enough, maybe you're starting your voltammogram at like 0. So let's say I go right to my, let's actually test this. Let's say if I start at 0 and I go to 0, I'm only sweeping from here to here, and I simulate it, I won't actually see it. In fact, if I even start at, say, positive 100 millivolts, and again, this is something that has a redox potential of 0, and I simulate it, I maybe barely am going to see any kind of reversibility in my peak. And that has to do with the heterogeneous rate constant of my system. Now, there are a bunch of other parameters that you can play with. You can play with the alpha. You can play with the diffusion coefficient. These are a bunch of other reasons why you may have irreversibility in your system. That was a lot, but hopefully that those are a couple things you can do to determine, do you actually have like a truly irreversible electrochemical system. Okay. This is good. Okay, moving on. Sini Suresh. While studying electrocatalytic reduction, ECR or ENRR reactions to understand a electrochemical system's efficiency, is it better to carry chronoamperometry or chronopotentiometry? Systems efficiency. I'm not 100% sure because I don't know if you are doing an electrocatalytic reduction, say CO2 reduction, and you're looking at the efficiency of the system, say the Faradaic efficiency, I actually think, personally, I think that doing chronoamperometry is the better way to determine the electrochemical efficiency. And the reason why, and let me share my screen. Also, just noticing that Dully says thank you. He'll try higher than 1 volt per second. That's a good start. And just thank you. So that's good. Okay, just making sure I'm keeping up with things. Questions. It doesn't look like there's anything on Twitter, which is good to know. So let me share again our Aftermath software. I'm going to hide your thing one more time. All right, so I'm sharing this again. Let me also just hide your question so you can see this. So one thing that we can do is I'm going to do a new, so actually I am going to pick bulk electrolysis because that's effectively chronoamperometry. And let's say I am doing, let's kind of reset this back to normal. So let me simulate this. And this is your reduction, the chronoamperogram, or the amperogram that you're going to get. So this is interesting. Let's see. Picoamp current, bulk electrolysis, 50 milliamps. And it's a reduction. Oh, I think in this case, I'm not adequately. So I'm applying a positive potential, but I think I'm doing a reduction. If I do this again, yeah, okay, this makes a lot more sense. Okay, so if I do so we'll do a reduction, and then I'll make this minus 50 millivolts. So you're actually getting a sufficient amount of current. But what you're going to want to do for your bulk electrolysis experiment, or this is really chronoamperometry, is what you'll do is you'll want to take this data. You'll need to kind of extract and remove things like double layer charging. And then you're going to want to take this data and you're going to want to determine the area under the curve. So let me show you this for actually an oxidation, just so that it's a little easier to see. Okay, so I'm going to take this. I'm going to archive this data. And then this is kind of the tabular results. I am going to look at the measured current as a function of time, because that's what we got. That's the chronoamperogram. And now I have this plot. Okay, this just gives me a chance to look at some of the tools that I have that are accessible to me. Well, what I can do here is I can now use a tool, the area tool. So if I go to add tool and then area, I have a little bit of wiggle room. I can now determine, hey, if I put this cursor here and maybe I zoom in, I want this to be around 0. All right, so I want this to be around 0. And I want to, have this thing go out for some period of, time, the length of the duration of my experiment, right? So I get this charge. And in this case, it's about 900 microcoulombs of charge. Well, if you're doing an electrolysis experiment, you can convert this number, and then considering the number of electrons that was transferred, in this case it was 1, but I could do it for a different amount. You would then take this number, and then you would look at how many moles of molecules should I have gotten for my reduction processor. In this case, it's an oxidation. And then I can then do something like a mass spec, where I actually can get the exact number of moles of my species, and then I can see, oh, the number of moles I got and then converted to coulombs of charge is actually half, which meant that my catalyst was actually 50% efficient. The charge, like half of the charge that I was using for my experiment, was going to a non-Faradaic process. That's not good, or it's not going to the product that I want. And this is possible with chronoamperometry or bulk electrolysis. I mean, they both do the same thing. They're both holding a potential and measuring the current as a function of time. But being able to determine the charge that passes, converting it to moles, and then looking at the moles that you get of your product, your specific product, from something like GCMS is really, really helpful. That can help you determine the efficiency of your electrocatalytic process. So, Sini, Suresh, I hope that was helpful. That's a way that you can use chronoamperometry as opposed to chronopotentiometry to determine the efficiency of your electrocatalytic system, electrocatalytic reduction. All right, let's see if I've gotten more questions. Let's see. Okay, so let's see. Mulunkin Eshtu, I think. I hope I'm pronouncing that correct. Let's see. I was doing copper manganese deposition on GDL. I did CV from -1.4 to 1 volt, but I couldn't see a reduction peak at minus 4.5 volts, and do chronoamperometry and found that only copper is deposited. So let's see. I think there's a continuation to this. And when I do cyclic voltammetry deposition for 20 cycles, I found out that copper manganese are deposited, but the deposition is very poor. What are your recommendations? Okay, so there are a couple things I like to mention. One is that originally, I don't know about this reduction peak at minus 4.5 volts. I feel like that has to be a typo because minus 4.5 volts is not within the minus 1.4 or 1 volt range that you said you did your CV experiments in. But I couldn't see a reduction peak for volts. So I found that only copper is depositing. So I think I would need to see a little bit more. Deposition was very poor. I think there's a couple things to keep in mind. I don't know enough about your system, and all I'm going to do is just give you maybe some general recommendations. But it is possible that copper and manganese don't deposit at the same potential. And there are a lot of, so there's the potential that you set, and then there's the cycles that you do. But one thing that I've heard of that's very helpful for people is actually doing a lot of different things in conjunction to the electrochemistry for the deposition. So for example, stirring the solution, or even rotating. Some people use a rotating disc for the deposition to control, say, something like laminar flow, is another thing that people do. So they're physically doing things to the solution to affect the mass transport of copper and manganese to the electrode, the GDL, which I don't know what that is. But you're just you're trying to deposit a metal onto another metal or another conductive material. So I think that you may need to play with two things. So let me share my screen to kind of illustrate what I think. All right, so let me delete all this. There's a couple things. There's a couple like parameters. I'm going to insert a text box. But basically the parameters to adjust, so there is CV cycles, and you can change things like the scan rate, and the potential window. Those are really the two things you can do with cyclic voltammetry. But you can also try a pulse or step technique as well. This is a case where you would say, so if this was like the voltage, this is the applied. Actually, no, sorry, that's time. So this is time. This is time. This is voltage, and this is the applied waveform. You may do something like this, something along these lines. You could do something like this, and you may want to change the frequency of these or the height of these. You may even try something. This is kind of like square wave voltammetry. Oops, this goes here. Something like that. There's differential pulse, and that's like a whole other thing. I don't actually remember the full detail of that waveform right now, but there's like other types of waveforms you can do to change how the deposition is occurring. You may also decide, if I have an electrode, right? And let's say it's like you have a shroud around it, some kind of shroud material around your electrode. You may decide rotating it. Some people do a rotating disc type of thing, generating laminar flow of solution. So doing something like this, or holding the potential while you rotate, or you can have like a stir bar in your solution that also rotates, and your electrode again is here, and this is just that's in your system. So you could use a stir bar as well. And of course, you have your counter, you have your reference. So those are a couple other things you can do. There are a lot of parameters that people use and try to adjust while trying to do depositions. So hopefully those parameters are things that you can adjust to try to improve the deposition of copper and manganese. And honestly, those are also parameters that you can use to adjust like the amount of copper, the amount of manganese. I mean, that's probably a whole research topic in and of itself. Let me see what else. Not sure. What did Chris say? Chris said, I'll add, need to be careful of secondary effects due to current density of thermal effects in practical systems. You probably need to run this at optimal current density. I don't know which comment that was for. Yeah, but also, thermal. You could heat your solution too, but that's another part of the deposition, another parameter you might be able to look at. Come in, let's see. With manganese copper, you're dealing with a number of oxidation states, so complexities and charge transfer are expected to in IIRC. Yeah. There will be a lot of complexities in terms of the deposition and how it works, but I'm just mentioning a couple parameters. I haven't actually done this kind of oxidation or plating before, so. Sorry. And Chris also says current density is also a consideration. Yeah, that's right, because the current density rather than just the current itself is also a very important aspect of it. Let's see. Looks like we got. I'm just checking to see if anybody mentioned anything, and it looks like we're good. So looks like there's no questions right now. I don't mind waiting a little bit longer. If there are any future further questions that come in, I'll have a sip of water in the meantime. Oh, the first comment was reference electrode. Was the reference electrode electrocatalytic reduction? Yes. Yeah, okay, that makes sense. Sure. Thank you. I will try that. Going with the same doubt, since there should be no net current at OCP. So why is there a need of a redox couple to define OCP? Like we can't define OCP for mercury, for like the mercury H plus and Br minus. Wait, let me read this question a little bit. Think about it. There should be no net current at OCP. So why is there a need of a redox couple to define OCP? You know, this kind of reminds. So in a way, OCP in many ways is a measure of redox couple potentials, actually, in a very strange way. So like reference electrodes, for example, if you have silver chloride, you're actually looking at the redox couple of like silver chloride be converting to chloride minus and silver plus, and there's a redox potential associated with that, and you could actually hook up reference electrodes, to your working to your counter reference in a 2-electrode manner, or just even with a digital multimeter, just plugging those two together, and the OCP measurement is the difference between those two redox couples. So a lot of people actually look at these redox couples, or just look at OCP measurements as like, well, it's just kind of the redox couple of whatever's in your system, and if it's stable or not. what's the potential difference between what your reference electrode is sensing versus what your working electrode is sensing. So I don't know enough about defining it for mercury H plus and Br minus, but you don't have to have a redox couple. Like OCP defines redox couples, and if your system isn't a very well established redox couple, then a lot of stuff happens. But that's actually kind of what OCP is looking at. It's looking at the potential difference between the open circuit potential between your two electrodes. It's easy to think about it in a two electrode system, but it's that potential difference between them. And the potential between these two things is governed by whatever is next to it in solution. And sometimes whatever is next to it, as one colleague says, it's dirt. It's it can be all kinds of random stuff. You're looking at the open circuit potential of dirt, and that's what it is. And dirt has a redox couple. Dirt plus electron equals dirt minus. So that can happen. Chris is actually responding to this as well. He says, a net current 0 does not imply that there is no current flow, just that they are confined to the cell and the electrons are not entering or leaving the system. Yes. So you can have a net current of 0, but oxidation and reduction reactions are both occurring in equal and opposite rates. And we have a funny word to describe that, which is equilibrium. So equilibrium, we sometimes use the word dynamic equilibrium. Stuff is happening. The forward and reverse rates are both occurring at the same time at the same rate. Not the same rate constant, but the same rate. That's another kind of important thing. That's just about equilibrium, just chemical equilibrium. But yeah, so that's one thing to note about net current. Net current equaling 0 doesn't mean that there's no current flowing. In fact, current does flow, but it can be equal and opposite. And what a potentiostat or what an instrument will record and tell you is just what the net current is. So that's why we use that term, that phrase. Again, let me check. Looks like nothing on the side of Twitter is happening. Let's see. So I think I'll wait just a few more minutes before to see if there's any more questions. Of course, every week it's always different. You can't say that everyone's always going to have electrochemistry questions every single week, especially at Fridays. But yeah, let's see. You're very welcome. Very welcome. Open circuit potential is actually a fairly complicated subject. It's kind of weird, and sometimes it's hard to fully wrap your head around, like, what does it mean? Like, what does the potential actually even represent? But that's why we have these live streams. We try to talk these things through, and Neil and I also learn a lot of new things. We don't actually know everything about electrochemistry. We just feel like we know enough that we can impart some of our knowledge to other people to kind of help them learn and understand some electrochemistry. And to us, it's worth it. It's worth it to do that for the electrochemistry community and society, because it's a hard subject. It's a pretty hard subject. Okay. All right. Well, been going for about just under an hour and a half, and I think that's a good kind of place to stop, unless some questions come in. That's fine. But let's see. Oh, yep, we do have a question. Let's see. Dillies, can an electron process that causes a reduction in a molecule cause a change in the geometry of the molecule, E over Z? Can this be seen as an effect in CV? So the answer is yes. The answer is absolutely. E over Z, I don't know about what E over Z is, But absolutely, when a molecule gains or loses an electron, it can absolutely change its geometry. One thing, an example I can tell you right now is carbon dioxide. So this is something I studied a little bit in graduate school. Let me delete all this stuff here. Carbon dioxide has a nice kind of linear geometry. It's like C double bond O. Okay. And it's got all these nice, like, electrons everywhere, valence electrons. But if you give it an electron, so plus an electron, and you reduce this is like in a non-aqueous solvent when there's no protons around. There is this kind of bent CO2 species. And actually, I think there may be another electron here. I can't remember. It's been a while since grad school, but I do remember that you do have, and maybe this is actually a single bond. Maybe there's a single bond here. And I think I'm trying to remember where the electron exists. I think maybe it's here. But it's like it's a minus anion radical somewhere. I forgot, maybe the electron's located here or something like that. But like the geometry changed. Holy cow, these two guys are super different. And that happens a lot in electrochemistry. In fact, the energetics, oh, let me see. He's just saying E versus Z is for double bonds. Yeah. So it absolutely can. Can definitely change the geometry of a molecule. It depends on the molecule. It depends if it's a metal. Ligands can come off if you have an inorganic complex. A lot of people suspect there's a lot of reorganization energy of like solvent molecules around it. So there's a ton of stuff that happens when an electron is injected or is put into or out of a molecule. So absolutely, the geometry can be there. I am actually a little bit curious, though, if you can comment more, like E versus Z for double bonds. I don't know. I also don't know what that means. I haven't heard of. Is E and Z just like we sometimes call them sigma bonds or pi bonds, or is E versus Z an orientation? Chris makes a very good point for extremes like protein conformation. Yeah, and proteins, they move around and they have these huge, massive structures. So and absolutely, that's a whole other field of like electrochemistry, is when you add or subtract. A lot of people are trying to look at even the UV vis spectral electrochemistry of a protein, and that's crazy. Oh, trans versus cis. Okay, yeah. So it can. I don't actually know enough if the stereochemistry. Yeah. Okay. So you're talking about stereochemistry. Okay. It probably can. I don't know enough about it, and I don't know if people have done things like optical polarimetry, like spectroelectrochemistry of optical polarimetry of like a specific molecule to see what if the orientation actually changes with the oxidized or reduced form of a molecule. All right, so Chris is just giving me a nice fun I'll throw down a topic for future contemplation: analytical electrochemistry. Wait, hold on. He has nothing. LCDs. Liquid crystal displays. They do. Well, I know about. I don't actually know enough about about liquid crystal displays, and if actually an electron transfer is involved to make the colors and stuff appear. Because like LCDs, I'm thinking about LCDs versus LEDs. LEDs is a different story. LCDs, liquid crystal displays. Yeah, I think that also. I don't know if that's like one of those like methyl viologen molecules and you apply a potential, it turns purple or blue or whatever to the area that it's contained in. I don't know enough about how some of these things work, honestly. But Chris said, just throw out a future kind of analytical electrochemistry. Well, a future topic. So actually, I would recommend going to like Jeffrey Dick, and he's at Purdue. He does a lot of analytical electrochemistry. There's like a ton of research. It's all about getting smaller and smaller electrodes. It seems like just can you make a nano electrode and use that to analytically measure certain things or measure nanoparticles on an electrode. Let's see. I'm trying to make sure I'm having fun. Just chatting with people at the same time if there is a question that comes up. Kind of like a Z molecule can switch to E and then chart and change the reduction potential seen in CV. Oh, let's see. Let's see. E. I'm gonna look up E and Z configuration. I'll have to look a little bit at it. Okay, yeah, cis and trans. Yeah, if it changes a double bond, it makes it twist in another way. I do not know about that. That is interesting. But yes, reorganization energy. That's all like Marcus theory for reorganization energy. Because solvents definitely have to reorganize, especially if it's a big molecule. So that's good. Yeah, analytical electrochemistry. Yeah, you can absolutely measure things. People are looking at like the limit of detection for a lot of molecules, special things. I mean, glucose sensors is a huge subject. Although that science has kind of been, I feel like it's been worked out pretty well. It's now other techniques that are trying to measure glucose, not just electrochemically, but like spectroscopically. Makes it easier to get accurate measurements. Okay. I think that's it. I think for just me, and no Neil, I think an hour and a half is pretty good. So I think I will call it. Wait, hold on. Just when I say I'm going to call it, it's like something comes up with it. What's this? I saw multiple oxidation peaks for reduction. Was only appeared once at minus 0.1, and I couldn't see another reduction peak even if I sweep to the potential until minus 2 volts. Yeah. Yeah, electrode deposition, it's just kind of, it's difficult. And I think he was responding to something Chris mentioned earlier. Yeah. I mean, it can be very complicated exactly like what the specific peaks refer to, and especially if you only see it once and you don't see another one if you do like say a smaller cycle. So actually, let me just demonstrate. One thing you might decide to do, Malokan, is if let me just make sure I am. Yeah, okay. So one thing you might decide to do is if I just erase. If I erase this, you may want to do some cycles, some CV cycles where it's like, so if this is voltage, this is current. You might decide like, oh, I'm going to do a CV like here. Then I do another CV up to like here or something. Then I do another CV up to like here, So the idea is you keep adjusting the potential window further and further to kind of give you a clearer picture about what's going on, because what you see in this region on the return wave will very much depend on how far out you push the potential. And that will give you a clearer picture about, oh, I have an irreversible reduction of copper on my electrode. Or I actually have reversible copper reduction. But when I go further out, something happens to the electrode surface and it's no longer reversible. Maybe you're getting, maybe you're getting like hydrogen evolution, or if you're oxidizing to, you're going to minus very large negative potentials for reducing stuff, you might be getting some other process occurring. So that's one recommendation, is just doing scans where you sequentially push out the potential window. It's kind of an idea. Let's see. You might have to keep going. Oh, like plus 7 oxidation states. Try to stay just. Yeah, that's actually a good point. Like, you have a complex soup of copper and manganese. You may decide to just do manganese and just study that and just see what that looks like. Oh, and it looks like so it sounds like Chris also has some information about getting manganese that's in a form that actually will deposit. Okay, so that's an important thing. Yeah, that may also. I didn't even think about the ligands on the manganese, or the state of manganese, its oxidation state, and then even what some inorganic complexes either have ligands that can easily detach so that you can easily deposit it, but also it may come as like a hydrate or a chloride, as just like a counter ion type of thing that's not part of the molecule, but it keeps its charge as a solid. So that's another thing. That's a very good point. I've done very little in the way of deposition. I've only done like a little deposition for making like screen printed electrodes, like depositing silver, and I don't know, we just use a very simple like silver plating solution. That's just what it's called, and then we use that and run another thing Vulcan you can do is run a galvanostatic experiment. So just tell the potentiostat to just apply like 100 microamps or 1 milliamp of current and just see what the potential is, and then see if like, okay, it's going to keep trying to deposit stuff on your solution or on your electrode, and it'll adjust the potential dynamically. And that way you can see, oh man, I actually need to apply like a way higher potential for something to happen or that to happen. But I think you have a lot of variables to say, you have a lot of variables to change, changing the solution, changing the pulse parameters, stirring, heating, so many things that you can do. But I'd try to simplify it first and then gradually make it more complicated. Hopefully that was helpful. All right, well, welcome to the stream. I'm going to find some questions on electrochemistry and KSP. Someone find your stream. Well, glad that you found us. If you have any questions, we're I'm happy to help. Although we'll be ending the stream probably somewhat soon. So Yuraja Sao, I can answer a question, or I can head out. We've been streaming for about an hour and 40 minutes or so. So. Any passivation taking place could cause issues as well. You may consider an asymmetric AC waveform. I have not. Yeah, maybe using EIS to see if you're having like you can look at film stuff like that. So, okay, interesting. All right, very good. Well, yeah, you're Vajsao. If you have questions, I'm happy to help. About electrochemistry and KSP, although, well, those are kind of related to each other. The equilibrium constant is related in the to the Nernst equation, and you can certainly get a equilibrium constant from the redox potential of your molecule. So maybe that's what you're asking for, or looking into. But let's see. Keep an eye out to see if anyone has made any comments. Twitter, or X, as they call it, just fine. All right. Okay. Let's see. Crazy terabyte. Can you explain the Nernst equation? Yes, I can. And let's see. Confused a lot. And you're just saying that I get confused with them a lot. Okay. So yeah, so let's talk about the Nernst equation. My favorite equation, and I just want to make sure I get the sign right, because I always kind of mess this up a little bit. But let me share my screen. All right, so let's talk about my favorite equation. Oops, what just happened? Let's talk about the Nernst equation. Come on. Lasso tool. Please erase all this. Okay, so the Nernst equation is something of the form that the potential is equal to the standard redox potential, E naught, minus, and just to double check, let's see, RT over NF minus. So RT over NF. And then that's the natural log of basically the activity, but I'm just going to put concentration of, say, oxidized over the reduced species. Something along these lines. This is the general form of the Nernst equation. So what does it mean? So this equation is then related to some redox reaction. Right? It's like some ox plus an electron is in equilibrium with red, the reduced state. This is the general form. Let me just make sure. They usually put something like Q, but it's products. Okay, so if it's Q, let me actually switch this so that it's more kind of technically correct, because you actually have products over reactants for being a quotient. So you would have red here, and then you have ox here. Products over reactants. Okay. So what the Nernst equation basically says is that the potential of your system that you're measuring, so if I have some kind of solution, I have these two, if I have, actually I don't even need to have two things in solution. If I have a reference electrode, which is just a known reference point in my system, and in this case, that reference electrode is the standard hydrogen electrode, SHE. That's what that is. And then I'm kind of measuring the voltage with a voltmeter. This is a really crummy drawing of a voltmeter. And then I have another electrode. And my redox reaction here is happening at the surface of my electrode. So that's what's happening. So all of the things about the Nernst equation have to do with things that are happening at the surface between these two species. And the potential that you measure is a function. This is, this E is what you measure. But it's basically a function of the natural log of the concentration or the activity of your species. So if you have more oxidized or reduced species, the potential is going to change, or it's going to shift ever so slightly. And this is evident in things like cyclic voltammetry. As you change the potential, we think about this in doing analytical chemistry. When you change the potential, which is what you do in cyclic voltammetry, you are literally changing the concentration of the oxidized and reduced species at the surface of the electrode. Your voltammograms that look like these ducks is a representation of the change in the concentration of the oxidized and reduced species. Conversely, you could also just have an electrode where you're not shifting the potential, change the concentration of these things around it, and you'll actually start to see the potential shift. So that's what the Nernst equation represents in a way. And so like reference electrodes, the potential of a reference electrode here, SHE, is based on the Nernst equation. It's hydrogen and protons with 2 electrons, and that gives you there's a potential associated with that, and we just call it 0. But that is what this, the Nernst equation governs that potential. So let me see if people have any kind of further questions about that. But that's the Nernst equation. I can talk about that forever because it's an interesting equation. Changing the bias of a sine pulse. So let me actually stop sharing. Changing the bias of a sine or pulse ratio. Now let's see. Good. I'm glad that you got a new perspective. So that's cool. Very good. Let me see if I can answer Chris's question. Changing the bias of a sine or pulse ratio for each direction can help deal with surface issues. So if you have so this is like a sine wave. So I'm just wondering if Pine stuff can do that. And yes, you can certainly ask me another question. You can ask me as many questions as you want. Whether I get to them will be another question. But yeah, I know, going back to the plating question, just being able to change the bias of a sine wave. We do have EIS, like we can do electrochemical impedance spectroscopy, and we can probably design something where we can apply a sine wave on top of a bias, and then we can start a new EIS experiment and then start a sine wave at a frequency at a different bias. But I don't know about changing it or changing the pulse ratio. Yeah, there's no way. I mean, we have the ability to. Let me show you how we can kind of think about this. But if you can see, and here we go. So if you can, so in EIS, let's just do impedance spectroscopy. You can change the EIS baseline. You can change what that is. You can change the amplitude here. You can even change the frequency and how many of those points you measure. But I don't think there's a way you can create a technique. And we have ways of creating frequency series or just a list of frequencies that we want to do. But I don't think there's a way, it'll always have the same amplitude. It'll always have the same EIS amplitude. But we can create, what you can do is you can create a sequence. And you can have one EIS experiment. And then let's just say I copy this and I do some other new stuff. And I can have 2. So I can create sequences of sine wave experiments with different pulses and not have things happen in between, so that the potential that goes from one experiment to the next, to the next, to the next. So our software can do some stuff like that. I don't know how helpful that is. All right, let's see. Let me see. All right, going through a couple questions. I know, sir, it's too bad. Sir, can you explain how concentration cell works? Please, my teachers couldn't explain it. Concentration cell. Are you just referring to what the concentration of a molecule or a species is in a cell or a solution? This is just a kind of a bit of just a bit of clarification. I just want to make sure I'm explaining the right thing to you. Oh, okay. So your brother is crazy terabyte. All right. So both of you are coming from the same place. So let's see. So my teacher didn't really teach me what it actually meant. Like, oh yeah. Oh, it's also possible. Oh, like, okay. So, oh wait, why is that not showing? Like SHE. Okay, so you're interested in like SHE. What is SHE? Okay, so all right. So we're going back a little bit to the Nernst equation, just a bit. I think. Let's see. Oh, okay. And you're in India, and you're trying to study for the Indian college entrance exam. Okay. All right. So we'll talk a little bit about this. So SHE stands for the standard hydrogen electrode. And let me just kind of go back to this presentation. We'll use the lasso tool here and get rid of all this. Well, you'll probably actually need this, so I'm not going to get rid of some of it. I'm only going to delete a couple things. So let's just delete that. So SHE, actually, I will tell you, I will do this because you guys can watch this video again later if you need to look at that again. So SHE stands for the standard hydrogen electrode. And there's a couple of things like SHE, NHE, stuff like that. This is what it really is. Okay. So this is the equation. I don't know why this is happening. It's like it was curving a little bit, my cursor. Plus 2 electrons, this is the reaction, is in equilibrium with H2. What's going on here? Oh. For some reason, my, hold on. I think my PowerPoint crashed for some reason. That was strange. Okay, let me get back to that. All right, so thank you. Great. I can also just do a new one just so that we can all see what's going on. All right, so let's go back to that. Okay, so SHE is this reaction. 2 protons plus 2 electrons. And Chris is correct there. There's a pH dependence, which has to do completely with this guy, is in equilibrium with hydrogen gas. Okay. So what is this physically, right? Like you see this equation and we call it 0. This is a E naught equal to 0. That's just because we define it that way. But what this is physically is because I did this in graduate school, I have a beaker of sulfuric acid. So let's just call it 1 molar H2SO4. That's what this is, like H2SO4. I got acid. That's what this is. Sulfuric acid. And I take a platinum wire. So this is a wire of platinum. This all happens on platinum. They don't mention that. So that's a platinum wire. This is PT. And then I have a little tube. It goes into this little solution here. And hydrogen gas is flowing into it. Okay? This whole system here is the hydrogen electrode. That's what it is. The potential of the platinum, right? This potential of the platinum is defined as 0 in this system, which represents this. It's interesting. So H plus from your sulfuric acid is gaining 2 electrons and it's becoming hydrogen. And the hydrogen that's bubbling into your electrochemical cell, little bubbles here, are getting on this platinum wire, and then they're converting back to 2 electrons and 2 H plus. That's happening. That is happening in your system. Both of these things are happening. and then in a dynamic system. Now, similarly, I have this whole setup, and maybe this is, let's say this is a little porous piece of glass, and it's electrically connected to another cell, right? I can put some other cell, some other like platinum or metal, let's say it's glassy carbon. I can have some other reaction happening here, like another electron transfer process happening. And there's a potential, a different reaction right here that's related to this. Like, and here's the important thing. So let me stop and just kind of look at you for a second. Potential is a relative quantity. In your chemistry class, you probably learned about Gibbs free energy. You probably learned of the equilibrium constant. And all of those are kind of these absolute quantities. Of course, at standard conditions. All right. So, oh, hold on. Where should be oh. We're not seeing your current drawing. Document recovery. Oh, man. Oh. Something Restream is confusing. Oh, damn. Okay. Let me start that over. I can do that again. Okay. So I'm going to now check again. All right. I drew this whole thing. Okay. All right. Great. Okay. Thank you. I can do this again. This is not a problem. All right. So let me... Wait a minute. I don't need to write this again. I'm just going to tell it to you. So, but I'm going to make it a little less confusing because there's a lot of stuff here. So let me just do this here. Okay. All right. Is everybody with me? Everybody, once more. Now you can see it. Okay, great. Great. Everyone can see it. Fantastic. All right. Technical hiccups. These things happen. Okay, so this is the reaction of SHE, standard hydrogen electrode. And we call it, that the potential of this is equal to 0. That's because the potential of this is related to itself. So let me illustrate. Let me give you the illustration of what this is physically. I have a beaker of concentrated sulfuric acid. Let's say it's 1 molar H2SO4. That's what that is. And maybe it's 1 molar. Might be higher, might be a little lower, but that's what it is. And Chris is correct. The pH is the measure of its concentration, right? So the pH is important because of the Nernst equation. It'll shift, but for now, that's not important. What I want you to understand is that this equation that just seems very arbitrary is really this physical system. 1 molar of concentrated sulfuric acid, and then I have a platinum wire that goes into my solution, and then I have a tube of gas of H2 gas that's bubbling into my solution. This whole system, everything that I draw, like you get this thing in the lab and you put it together, this represents this equation that you see. That's the standard hydrogen electrode. Now let's make sure that nothing broke and people can see things. Good. All right. I'm just checking. Now, what people... So this definition of 0 is arbitrary. We just decided that we're going to call this 0. And we call it 0 because whenever we reference something, and this is the thing about potential, right? And so if I stop sharing and I can look at you, potential is a relative quantity, right? So unlike things like Gibbs free energy and the equilibrium constant, those are kind of absolute quantities. Like there's a K, there's a delta G. It's like it's a number. But potential is relative. It's with respect to something. So even in India, the wall outlets that you have there's a voltage coming out of it. It's AC. Maybe it's like 50 hertz. but there's a voltage that comes out of it. That's with respect to ground. We say maybe 120 or 240 volts, but it's with respect to ground. Ground is the reference point. In electrochemistry, we have arbitrarily said that it's standard. That's the standard. We're going to call platinum standard. So whenever you're looking at any kind of redox reaction where it's like copper 2 plus electron gives you copper 1 plus equals E naught equals some number, some value, that's with respect to SHE. So that's what it is. That's a way you could kind of physically wrap your head around what it is. So I think I've answered the question, which is what is SHE? Okay. Is that what is he saying actually about power systems? Well, in power systems we're usually talking about phase voltage unless we're in the US. Oh. So actually, Chris, I heard from our electrical engineer that there's this whole like 2-phase, 3-phase electric, and I don't know anything about that, like how it works or how it makes sense. I assume it has a little bit to do with the fact that it's AC and the fact that there's a phase delay or a phase lag, which is why it works. But that's something I actually might be interested in looking up at some point. So does Uraj Saw and Crazy Terabyte, does this kind of make a little bit of sense? I hope it makes a little bit of sense. I mean, that's what it is. And hopefully your conceptual understanding kind of makes sense. Explanations are going to sleep. It's 1:30 a.m. Okay, yeah, 1:30 a.m. in India. Well, have a good night. Get your sleep. Good luck on your entrance exam. All right. And subscribe to the Pine Research YouTube channel because we're pretty cool. And you have questions, we'll try to answer them, if of course they're electrochemistry related. All right. Oh, multi-phase power. I will look in. I am a little curious but at the same time, I think I'm gonna be like totally like not gonna understand what it is, but stuff like that. Okay. All right. Have a good night, you guys. Or good day or good morning. I think it's still morning for you, Chris. Maybe. But all right. Have a good one, and I'll see you guys soon.